Welcome to all. Here we define the residues. After defining residues, to evaluate the definite integral using residues theorem, first we define residues, and before defining residues, now we have to know that isolated singularity. A point A is called an isolated singularity if the function f of z is analytic except at a point in the neighborhood of A. So we know the isolated singularity definition. Define residues. Let A be an isolated singularity for f of z. Then the residues of f of z is the Lorentz series coefficients, the coefficient of 1 by z minus A, and is denoted by residue of f of z comma A equal to 1 by 2 pi integral over c f of z dz, that is b1. The Lorentz series coefficient of 1 by z minus A. So, example, calculate the residues of e power z by z square at its poles. E power z by z square, let f of z equal to e power z by z square. Here pole is 0. Since z equal to 0, the function is not analytic. Therefore, e power z by z square means z equal to 0 is a double pole. E power z by z square, expand this function as Lorentz series. So e power z by z square, 1 by z square, e power z expansion 1 plus z by 1 factorial z square by 2 factorial plus up to etc. Here f of, therefore 1 by z square plus 1 by z 1 by 2 factorial up to etc. Z square bracket removing, we have find the values. So f of z, since 1 by z square 1 by z, therefore the maximum value is 1 by z square denominator value. So therefore z equal to 0 is a double pole. Since residue means the 1 by z minus a coefficient. So 1 by z minus a means here is a equal to 0. Therefore 1 by z coefficient is 1. Therefore residue of f of z comma 0 is a coefficient of 1 by z, which imply 1. And lemma. So here defining residues for some particular points. So yeah, z equal to a is a simple pole, then residue of f of z comma a equal to limit z tends to a z minus a into f of z. Let f z equal to a is a simple pole for f of z. Then the Lorentz series expansion about z equal to a is given by, so z equal to a is a simple pole, therefore we go to f of z is b1 by z minus a plus some power series of z minus a. So here b1 by z minus a. Now to find the residue of f of z comma a, therefore limit z tends to a z minus a into f of z. Now z minus a into f of z equal to b1 plus a naught into z minus a plus a1 into z minus a the square up to etc. So which imply limit z tends to a z minus a into f of z equal to, here b1 is the only term and the remaining terms are equal to 0. So therefore b1 is the residue of the coefficient of 1 by z minus a in Lorentz series expansion, which imply b1 is the residue of f of z comma a. So limit z tends to a z minus a into f of z equal to residue of f of z comma a. Another lemma, let a be a simple pole for f of z and f of z equal to g of z by z minus a. F of z is a function of g of z by z minus a, where g of z is analytic at a and g of a not equal to 0. Then residue of f of z comma a equal to g of a. Now let f of z equal to, given f of z equal to g of z by z minus a, where g of z is analytic and g of a not equal to 0. Now residue of f of z comma a by lemma 1, residue of f of z comma a equal to limit z tends to a into z minus a by into f of z. So f of z means g of z by z minus a. So g of z by z minus a cancel, limit z tends to a into g of z. So therefore z equal to a g of a. So therefore residue of, if f of z is a function g of z by z minus a, then residue of f of z comma a equal to g of a. And another lemma A be a simple pole for f of z. A be a simple pole for f of z, and f of z is a function of f of z is of the form h of z by k of z, and where h of z is k of z are analytic at a and h of a not equal to 0. So residue of f of z comma a equal to h of a by k dash da a. Now residue of f of z comma a equal to limit z tends to a into z minus a f of z by lemma 1. F of z can be written as the h of z by k of z. So therefore limit z tends to a z minus a into h of z by k of z. Therefore h of z limit one expansion. So limit z into a h of z into limit z tends to a z minus a by h of z. So h of z is always same, and k of a equal to 0. We have to define k of a equal to 0. So therefore limit z tends to a h of z into limit z tends to a z minus a by k of z into minus k of a. So this is the expansion for 1 by k dash of z. Since k dash of z equal to k dash of z equal to limit z tends to a k of z minus k of a by z minus a. So therefore z minus a by k of z minus k of a equal to 1 by k dash of a. Therefore residue of f of z comma a equal to h of a by k dash of a. And suppose if f of z is a f of z is can be written as g of z by z minus a power m. Here a is a pole of order r. That is g of z is analytic at a and g of a not equal to 0. Residue of f of z comma a equal to g power m minus 1th derivative of a by m minus 1 factorial. Now here by higher derivative definition, g power m minus 1 power a equal to m minus 1 factorial into 2 pi I into integral 0 to integral c f of g of z by z minus a power m into dz. So here c is the circle. Here m minus 1 go to left side. So therefore g power m minus 1 into g power m minus 1 of a by m minus 1 factorial equal to 2 pi I into integral over c f of z dz. This is nothing but residue of f of z comma a. So therefore residue of f of z comma a equal to g power m minus 1 power of a in by m minus 1 factorial. So therefore if f of z, there is three lemmas. First one is a is a simple pole, then residue of f of z k z comma a equal to limit z tends to a into z minus a into f of z. Suppose in here also second one, a is a simple pole and f of z can be written as the g of z by z minus a. Then residue of f of z comma a equal to g of a. And third one is a is a simple pole, then residue of f of z comma a equal to, suppose a f of z can be written as the h of z by k of z. Residue of f of z comma a equal to h of a by k dash of a. And the last one is a is a pole of order m, then f of z equal to g of z by z minus a, which imply residue of f of z comma a equal to g power m minus 1th derivative of a by m minus 1 factorial. Using lemmas we have to derive some examples. So first example, z plus 1 by z square minus 2z, find the residue of its poles. First we have to find the function poles at the function f of z. So here f of z equal to z plus 1 by z square minus 2z. So expansion of z square minus 2z equal to z into z minus 2. Therefore here z equal to 0 and z equal to 2 are simple poles for f of z. Now to find the residue of z plus 1 by z square minus 2z as it poles. So first residue of f of z comma 0. Here function z plus 1 by z into z minus 2. So here z is equal to 0 is a simple pole, either first lemma or second lemma. So limit z tends to 0, z minus 0 into, first using lemma 1, z plus 1 by z into z minus 2. So z minus 0 cancel, and remaining value z plus 1 by z minus 2. So z tends to 0. So the two z's are 0, 1 by minus 2, which imply minus 1 by 2. And the second one is residue of f of z comma 2. Again the same level, z tends to 2, z minus 2 into z plus 1 by z into z minus 2, z minus 2 cancel, z plus 1 by z. So 2 by 2 plus 1 by 2, that is 3 by 2. And remaining the same way, 1 plus z, 1 plus e power z by z into cos z plus sin z. Here the poles, first we have to find the poles of z plus function f of z. So to find the poles, z cos z plus sin z equal to 0, which imply for what values of z cos z plus sin z equal to 0? Yes, clearly 0 is the only value. Here clearly 0 is the simple pole of for f of z. So therefore residue of f of z comma 0. Here we have to using lemma 1 does not applicable. So therefore using lemma 3. So let h of z equal to 1 plus e power z and k of z equal to 1 z cos z plus sin z. So therefore residue of f of z comma 0 equal to limit z tends to 0 h of z by k dash of z. So k dash of z equal to differentiating k of z, z cos z plus sin z. Therefore uv method, z into cos z differentiation minus sin z. Therefore minus z sin z plus cos z plus sin z. So residue of f of z comma 0 equal to h of 0 by, here h of 0 by k dash of 0. h of 0 by k dash of 0. h of 0 is nothing but 1 plus e power 0 by minus z minus 0, first term 0, second term 2 cos 0. So 2 cos 0 equal to 2. So numerator 2, denominator 2, answer is 1. And fourth example, find the residue of 1 plus z square plus a square by 1 by z square plus a square the whole square at z equal to a. Clearly z equal to a is a pole, and first we have to find f of z equal to 1 plus z square plus a square the whole square, expanding z plus a the whole square and into z minus a the whole square. So clearly z equal to ai, here z equal to a value 0 and z equal to minus a value 0. Here power is 2, therefore a and minus a are poles of order 2. So poles of order 2, which imply we have to use lemma 4. So g of z equal to 1 by z plus a the whole square. Here pole is equal to ai. So ai. So z equal to 1, g of z equal to 1 by z plus a the whole square, and g dash of z equal to minus 2 by z plus a the whole cube. Therefore residue of f of z comma ai. Now to find the residue of z equal to a only, now suppose z equal to a is not given, then we have to find z equal to a pole residue of z equal to a and z equal to minus a. So here now here to find z equal to a poles only. So therefore g of z equal to 1 by z plus a the whole square. So which imply g dash of z equal to minus 2 by z plus a the whole cube. Residue of f of z comma a equal to g dash of a by 1 factorial. So 1 factorial value 1. Therefore g dash of a value, a means minus 2 by my a plus a the whole cube, that is 2a the whole cube. 2a the whole cube equal to 8 a cube I cube. 8 a cube I cube equal to I square value minus 1, numerator value minus 2, minus cancel. So 2 by 8 a cube I, which imply the denominator I becomes numerator minus I by 4a cube. Another example, find the poles of z square plus 4 by z cube plus 2z cube plus 2z. Here to find the poles, first we have to find the poles and we have to find the residues. So to find the poles, z cube plus 2z square plus 2z equal to 0, and the expansion of zq plus 2z plus 2z equal to z into z plus 1 minus I, z plus 1 plus I. So therefore the poles are z equal to 0, z equal to minus 1 plus I, and z equal to minus 1 minus I. So therefore the poles are z equal to 0, minus 1 plus I, minus 1 minus I are the simple poles are f of z. Now here z square, numerator and denominator are functions of z. So therefore we have to use the lemma f of z equal to h of z by k of z, where k of z equal to z square, sorry, h of z equal to z square plus 4 and k of z equal to z cube plus 2z square plus 2z, and k dash of z equal to 3z square plus 4z plus 2. Therefore residue of f of z comma 0 equal to h of 0 by k dash of 0. Simple. So h of 0 equal to 4 and k of 0 equal to k dash of 0 equal to 2. So therefore 4 by 2 answer is 2. Next to find residue of f of z comma minus 1 plus I. Therefore h of minus 1 plus I by k dash of minus 1 plus I. So z square plus 4. Therefore h of z equal to z square plus 4, which imply minus 1 plus I the whole square plus 4, k dash of 1 minus 1 plus I. So k dash of z equal to 3z square plus 4z plus 2, and substituting z equal to minus 1 plus I. Here simplification, after simplification we have to find the value of residue of minus 1 plus residue of f of z comma minus 1 plus I equal to 3I minus 1 by 2. Similarly we have to find residue of f of z comma minus 1 minus I. So another example, let's find the residue of cot z at z equal to 0. Here cot z, f of z equal to cot z. Cot z means cos z by sin z. Again cos z by sin z is a function of z. So therefore f of z equal to h of z by k of z. Here k sin z tends to 0 at z equal to 0. So therefore z equal to 0 is a simple pole for f of z. So f of z, say z equal to 0, then residue of f of z equal to h of 0 by k dash of 0 is equal to cos 0 by k dash of z. Sin is k of z equal to sin z, therefore k dash of z equal to cos z. So cos 0 by cos 0, value 1 by 1, that is equal to 1. Here e power z by z square into z square plus 9. So f of z equal to e power z by z square into z square plus 9. Clearly 0 is a double pole, that is 0 is a double pole, and 3i minus 3i are the simple poles. To find the residue of f of z comma 0, so here double pole means using lemma 4. So g of z equal to e power z by z square plus 9. G of z is analytic at z equal to 0 and g of 0 not equal to 0. Therefore g dash of z, here g dash of z is u by v method. So u by v method, e power z into z square plus 9. So 1 by z square plus 9. U by v method application to g of z equal to, after simplification, g dash of z equal to e power z into z square plus 9 minus 2z by z square plus 9 the whole square. Therefore residue of f of z comma 0 equal to g dash of 0 by 1 factorial using lemma 4. So z equal to 0 means e power 0 1, 9 minus 0 by 9 square. So therefore 9 by 9 square, 1 by 9. Answer. Residue of f of z comma 3i. F of z comma 3i. 3i is a simple pole. So therefore f of z equal to h of z by k of z. So therefore residue of f of z comma 3i equal to h of 3i by k dash of 3i. So here h of z equal to 3 e power z and k of z equal to z square into z square plus 9. Simply k dash of z equal to 4z cube plus 18z. So simplification, h of 3i equal to e power 3i, k dash of 3 equal to 4 into 3i the whole cube plus 18 into 3i. So therefore e power 3i means cos 3 plus I sin 3. And simplification, we have answer is cos 3 plus I sin 3 by minus 54i, and I denominator value. So therefore go to numerator residue of f of z comma 3i equal to I into cos 3 plus I sin 3 by 54. Similarly, we got to find the residue of f of z comma minus 3i. Another example, f of z equal to e power 2z by z minus 1 the whole square. Here, find the residue using the Lorentz series expansion. So first we got to expand f of z as a Lorentz series. F of z equal to e power is 2z by z minus 1 the whole square. Here z equal to 1 is a pole of order 2. So is expand Lorentz series at z equal to 1. So e power 2z, here e power 2z is equal to e power 2 into z minus 1 plus 1 bracket. So e power 2 into z minus 1 plus 2. So e power 2 into z minus 1 into e power 2 by z minus 1 the whole square. So e power 2 is a constant. E power 2 into z minus 1 expansion equal to 1 plus 2 into z minus 1 plus 2 square into e power z formula is 1 plus z by 1 factorial plus z square by 2 factorial plus z cube by 3 factorial up to etc. So after removing the bracket, e square into 1 by z minus 1 the whole square plus 2 into z minus 1. Therefore, here z equal to 1 is a pole of order 2. Here, using Lorentz series expansion, residue of f of z comma 1 equal to the coefficient of 1 by z minus 1 in the Lorentz series expansion. The coefficient of 1 by z minus 1 is 2 into e power 2. So, residue of f of z comma 1 equal to 2 into e square. Yeah, z into e power z by z minus 1 the whole cube. F of z value. So, clearly z equal to 1 is a triple pole. That is pole of order 3. And g of z equal to, therefore using lemma 4. So, g of z equal to z into e power z. And g dash of z equal to z e power z by z into z plus 1. G double dash of z. So, residue of f of z comma 1 equal to pole of order 3. Therefore, g power m minus 1th derivative of a by m minus 1 factorial. So, g double dash of 1 by 2 factorial, that is equal to g double dash of 1 equal to e power 1 into 1 plus 2, that is 3 into e by 2 factorial value 2. Answer is 3 into e by 2 and 1 by z in minus sin z. So, to find the poles of f of z, z in minus sin z expansion, z into z minus 3 square, z cube by 3 factorial plus z by 5 by 5 factorial minus up to etc. So, z cancel, remaining value z cube. So, z cube after expanding, z cube into 1 by 3 factorial minus z square by 5 factorial plus etc. So, clearly z equal to 0 is a pole. Here 1 by z minus sin z. So, therefore, z minus sin z tends to 0 at z equal to 0. Here z equal to 0 is a pole of order 3. So, using lemma 3, lemma 4. So, g of z equal to the values after removing the poles, g of z equal to 1 by 3 factorial plus z square by 3 factorial. So, z equal to 0 is a pole of order 3. Therefore, residue of f of z comma 0 equal to g double dash of 0 by 2 factorial. So, here differentiate with respect to z at 2 times. Clearly, g of 0 equal to 6. So, differentiating 2 times is very difficult. Therefore, first we have to find g of 0. G of 0 equal to 1 by 6 and now g 1 by g of z equal to reverse procession. 1 by g of z equal to 1 by 3 factorial minus z square by 5 factorial. So, differentiating with respect to z, we have g dash of z by u baby method. So, g dash of z by g of z the whole square. Here differentiating minus 2z by 5 factorial plus 4z cube by 7 factorial minus up to etc. Hence g dash of 0. Now g dash of 0 equal to 0. So again we have to different. So we have to find g double dash of z. Therefore second derivative differentiating with respect to z, u baby method, g of z square is expansion So right side equal to minus 2 by 5 factorial plus 4 is 12z square by 7 factorial minus etc. So here we have to find the values of g of z and g dash of z at z equal to 0, g of 0 equal to 6 and g dash of z equal to 0. Therefore substitute the values, we get g minus g double dash of 0 by 36 equal to minus 2 by 5 factorial. So therefore g double dash of 0 equal to 3 by 5, which implies residue of f of z comma 0 equal to g double dash of 0 by 2 factorial, that is equal to g double dash of 0 3 by 5 into 2, that is 3 by 10. Hence the problem. Thank you.